Hey students, welcome today to equilibrium. Remember you were supposed to read this first little section on your own, so we'll skip that for this video and we'll kind of just jump right into equilibrium constants. So first off, we have our equilibrium constant K. This is the ratio of products to reactants. And we'll see that, and so the other thing we should say at equilibrium. So we're talking about our ratio of products to reactants when we're at equilibrium. All right, kind of trailed off there, but you'll be okay. So what we have is called the law of mass action, and this is where we start from there. So we have an example of just a generic equation, and to write our equilibrium constant is, we say K, because that's our constant, and we'll have some little subscripts in this throughout the rest of the way, but for right now, we just roll with K, all right? And what we do is we take products over reactants, and each is raised to their moles. So if we take our products, remember our products are on this side, so we're going to take the concentration of big C raised to the power of little c times the concentration of D raised to the power of little d, and then we have over the concentration of A raised to the power of little a times the concentration of B raised to the power of lowercase b. Pretty simple, hopefully, and that's how we figure this out. So what we're going to do is we're going to write the equilibrium constant expression for this example. So let's see if we can't put that into play. Again, we start with K, all right? And we're going to say products over reactants. So we've got K, and then we have NO2 raised to the fourth, and then O2 raised to the first, or we could just leave it like that. And then we have N2O5 raised to the second power, or squared. All right, pretty simple there. So now that we know it's products over reactants raised to those coefficients, we can actually kind of dig a little deeper in K there, and we'll talk about our significance of the equilibrium constant. So if K is less than 1, much less than 1, so we're thinking the reaction or the reverse reaction is favored, or we think we're going to have lots of reactants at the end, right? Lots of reactants, and I should not say at the end, we should say at equilibrium, which makes sense, right? Because if we have a really small number, that means we're dividing by a bigger number on the bottom, right? Then we have K equaling 1. This does not happen very often, but then we have neither direction is favored, and we kind of have about the same ratio of products to reactants, right? Our ratio of products to reactants is pretty similar. All right, and then if we have K is greater than 1, the forward reaction is favored, and we would say that this one isn't, so this is a complete reaction. All right, so it goes to completion, or we have lots of products. All right, kind of going back up to the other one. Another one that we would say is that it's sometimes we have an incomplete reaction up here on this one. Incomplete. So we don't get very many products, so it is incomplete. And kind of our focus is on these here, because we don't really care, like when HCl dissolves in water, it goes to completion and we get all H's and all Cl minuses. That really doesn't affect much in our calculations, but we worry about these because there's different concentrations, and so we have to do a little extra work. All right, so let's kind of talk about how to manipulate K, because we can manipulate K kind of like we did with Hess's law in our thermodynamics just recently. So if we reverse the reaction, so if we flip it, our K will be inversed, right? So we'll be the inverse of it, right? So we take 1 over it to get there, right? Now, if we multiply the coefficients in the equation by a factor, we have to raise them to that power then, all right? And last but not least, if we have 2 or more individual reactions that we add together, we will just take K1 times K2, right? We multiply them together to get our Ks. So that's the first part of this, but we're also kind of continuing on this road because these next 2 are pretty short here. So, the first one we wrote was like K sub C, right? Up here, this K sub C. All right. We can also write it in terms of partial pressures because a lot of times we do that. All right, so we have our partial pressures. And so we do the same thing, K sub P equals, so we're going to take the partial pressure of SO2 squared times our partial pressure of O2 raised to the first, or just right there, over our partial pressure of SO3 squared. Pretty simple. It's the same thing. We just put partial pressure out front, and we did that because we had gases right there. We'll actually take this a little bit further in just a little bit. The last thing there is actually a relationship between Kp and Kc, so you can relate them to each other and move them from there. Unfortunately, this is no longer on the exam, so we don't really have to worry about it that much, but I do like to introduce it to you because I just don't want you to be surprised if you go on and take chemistry in college. And so now we have Kp, that makes sense, Kc makes sense, R is our gas constant, that's our 8.314. All right, T is our temp. That's got to be in Kelvin, right? That's our Kelvin temp. Our delta N is our change in moles of gas. All right, so if we kind of use that upper one as an example here, so there are 3 moles of gas on the product side and 2 on the reactant side. So for that one, we would take 3 minus 2 to calculate our delta N, if that makes sense. Awesome. Okay. Now units of K, this is just something that comes up. There are no units on K. All right. The very simple explanation of that is that it's based on activities. And that's kind of out there, but you can either think that there's no units on K and just kind of not worry about it, or you could say that it's based on activities. And kind of the way I think of activities is, this may not be 100% right, but it's distance from one, or distance on the number line. You know how those don't have labels, right? That's kind of what we're talking about there, kind of, like I said, in a very simplified formula. All right, and the last thing that we're covering in this video is our heterogeneous equilibrium. Sometimes we're going to have solids and liquids. So far we haven't seen that, but sometimes we're going to have solids and liquids in our equilibrium equation, and the key here is, boom, they do not, hit the eraser, these do not show up in our equilibrium equation, and the reason for that, if it's a pure substance, their concentrations don't change. All right, they don't change in concentrations because they are pure. And so if we use it, like if we're thinking of a solid, right, and we think about concentration, which is moles per liter. So as we use up moles, right, our volume goes down. So it's kind of in a little relationship like that. All right, so let's practice doing this when we have a solid or multiple solids. So remember, we take products over reactants. So we've got Kc, and honestly, the only thing we have is CO2. All right, these are both solids, so they do not show up in our overall equation. So we could just say Kc is equal to our concentration of CO2. And that is it. Pretty self-explanatory. All right, see you next video.